Hello everyone. So today we will be starting with statistical concepts and market returns on the CFA level 1 curriculum. So let's move along with what basically statistics talks about. On a broader note, if you look upon to it, so there are two broader statistical methods that we talk about. One is descriptive statistics and the other one is inferential statistics. When it comes to the descriptive statistics, what we basically deal is large data sets, maybe an entire population in terms of the data that we would like to study across. So we talk about a large data set into it, and or the population findings. Population findings from the statistical per se are referred as population parameters. Two of the broader parameters of the population could be population mean is denoted by mu and population standard deviation is denoted by the sign sigma. On the other hand, it becomes at times difficult to study and move along with the entire population as a data set. Maybe gathering the data is pretty difficult and studying the data becomes that much more complex also. So majorly researchers deal with taking a sample from the population. That's where we talk about the inferential statistics. You take small samples from the entire population. Samples findings are then referred as sample statistics. Two of the common sample statistics could be the sample's mean is denoted by x bar and the sample standard deviation is denoted by small s. Now why maybe inferential statistics? Because from this samples finding we make inferences about the population. That the sample mean is x, so the population mean could be this. So based on samples finding we make inferences about the entire population. Now as far as dealing with data is concerned, when you talk about dealing with a huge amount of data, if we can scale it down, it becomes that much more easy to study the data and to relate the data. So let's talk about various types of scales that we have. So there are four broader types of scales when it comes to data segregation. One of the first and the simplest scale is the nominal scale. When you talk about a nominal scale, it's simply putting similar characteristics things into a group and giving it a name. So let's say we are talking about stocks categorized as large cap, mid cap and small cap based on their market capitalization. Or let's say debt or equity, or maybe it could be based on maybe candidates pursuing graduations, candidates who are going for let's say an MBA product or an MS or maybe a CFA. So we've just selected certain data points with similar characteristics, put them into a bucket or basket and given that as a name, and that's what is nominal scale all about. One thing very important along with the nominal scale is duplication has to be avoided. So a single data cannot be into two segments or two clusters, let's say. So you got to have one data point into one particular cluster. But there is a limitation with regard to the nominal scale is that we are not giving any ranking as such, that large cap are better than mid cap stocks or maybe mid cap are outperforming the small cap stocks or so. So we have given just names based on the characteristics of the data points and put them into a cluster. On the other hand, the second scale could be a nominal scale where you do give ranking also. So let's say we say A is greater than B, which is again greater than C. So there is a ranking which is here, given here, but quantification is not there. So by what amount is A greater than B need not necessarily mean that B would be greater than C by the same amount, or else let's say we have not quantified. We can give the ranking but we have not quantified it. A simple example could be maybe at times utilities or satisfactions are measured on an ordinal scale. Let's say you go and watch a movie, you feel satisfied, and you watch another one, you can give a comparison that which one is a better movie as per you, but you cannot quantify like this is $5 more better or maybe $10 more better. So quantification is not there into an ordinal scale, but yeah, we can give ranking into an ordinal scale. The third one is an interval scale, which is one of the most important scales when it comes to statistical concepts and its utility in financial decision making. this is something which is very commonly where we put your data into different intervals. Let's say if you're talking about returns over past 20 quarters of companies, or maybe EPS of a company over the past 20 quarters, or maybe stock returns. So basically you put them into a range, let's say from minus 20% returns to minus 10%, then maybe minus 10% to 0, and then 0 to let's say 10%. That is how intervals are framed, and then you put the tallies into it. Let's say how many observations are coming across. So if we have just 3 subsets, let's say we have close to around 10 observations. That's how tallies are done. If you put it on absolute terms, it is 3, 5 and 2. On a relative measure, you can say 30% of data is coming between minus 20 to 10, and another 50% is coming between minus 10 to 0, and about 20% data is coming, and that into the 0 to 10 vertical. So that's where you can give a relative weightage to the data in terms of the outcomes. What portion of a particular data lies into a particular range, and that is where it becomes a very handy tool. Let's say if you want to know in the past what is the probability of, let's say, getting a negative return. So in this example we could say, let's say 80% of data has come below 0, so there is an 80% chances that this could be replicated in future also, if we take past as a basis to determine the future. So one of the most important scale is interval, but again, in this scale a precise comparison of two outcome is not there. Like if A is greater than B, by what percentage, or precisely by what quantification is A greater than B? And for that we might have to go to one of the most efficient scales, that is a ratio as a scale, where you can always say that A is twice as good as B, so A upon B is basically 2:1. Right. So when it comes to ratios as a scale, that is the most precise scale. We can say A is better than B, and we can quantify it also by what amount is A greater than B. Now invariably by this time a question definitely comes to candidates or people coming into the CFA curriculum. Why are we required as an investment analyst to go through with the statistical concepts? What is the significance of studying statistics to us? So a straight thing is, whenever it comes to an investment decision, there are two broader objectives. One is the return that you're supposed to get from it, and the risk aspect, and that is where statistics comes pretty handy to it. If let's say I ask you this thing, you want to anticipate a return from an investment, how do you go about it? How much should you expect, let's say in terms of a return from a stock like Google, or how much do you expect in terms of a return from, let's say, a property or a real estate, or maybe what is a return that you can expect by investing into gold? One of the way to determine is to look into the past. See, on an average, maybe in the past 15-20 years, this is kind of an average return that Google has generated or gold has given to the investors, and that could become a very good base to determine the future expectation about it. So let's look upon to what are various statistical tools that we can use, or concepts that we can use to make an inference about return anticipation. So let's talk about them one by one. So on the first front, you have the arithmetic mean, which is simply summation xi divided by n, which is sum of all the possible outcomes in the past, and then divide. So we basically taking past as a basis to anticipate the future, and what we are doing is, let's say past 15 years, this has been the return. So we have taken an average of that, and we say we could expect this in future. So if we talk about arithmetic mean, it's pretty simple to calculate and interpret also, but there could be certain problems with it. Let's see what could be a possible problem with an arithmetic mean calculation when it comes to return anticipation. Let's say your data points are like 3%, 2%, or maybe 4%, another 2%, or let's say 5% or 6%, and if you have taken an average and you say this is what I have got in the past and I anticipated, it's all fine. But if let's say in your data points you get a return which is, let's say, plus 50% or maybe minus 50%, so your average could come pretty high to the broader range that you have had, or pretty low to the broader range also. This extremely high values and low values are referred as outliers. So the broader thought is, outliers can distort your mean based expectation. You may not take 15% in this case, which is coming maybe your average, as your expected return, because you see that the broader data is into a different range. And that is where we move from, let's say, mean to median, where you calculate your median as n plus 1 by 2th term. So you arrange the data from descending to ascending, and the mid position value is basically your median. So if we talk about this entire outlier data only, if there is an extreme high positive value or low negative value, they will come at the extreme corners only, and they cannot be the midpoints. So at some point, or let's say to a certain extent, median does resolve that problem of outliers which is there with the mean, and you could have a better anticipation of an expected value. But then let's say if your data is distributed into a different manner, something like this, where there is high frequency of data here and high frequency of data here, but at the midpoint there is very low frequency of outcomes. And that is where median, which is saying that the mid value is your expected value or could be the expected value, may not resolve, might have its own cons also. So when we talk about this, the other thing could be going to mode as a calculation method, wherein we look upon to the maximum number of observation that has occurred. So in this example, this could be, let's say, 2 is your mode. Another problem which could be with 2 is, with mode is, let's say if you have another value, let's say 4%. Now you have two modes. 4% is a mode and 2% is a mode. So a data can have multiple modes. This is a bimodal data. You could have multiple modes into a particular data set, and which to take maybe an expected value again becomes a difficult aspect to determine. So every measure, like we've talked about the arithmetic mean, median, mode, they have their own benefits as well as limitations also. At times can analysts do this thing also. They determine the mean, median, mode, take an average of it and say this is my expected value. So that is another way of going ahead with it. Let's talk about other measures of expected return. So among the other measures of maybe determining the expected return, we can go ahead with a weighted average kind of a thing. So if let's say you have data points like 4, 9, 5 and maybe 10, so your average will be 4 plus 9 plus 5 plus 10 divided by 4. Let's say the value is coming as 7. But what does the weighted average talks about is pretty much similar to arithmetic mean. In an arithmetic mean, we are basically taking equal weights, which is, let's say, 1 by n or 1 by 4 in this case. And in a weighted average thought, we say every outcome has its own different probability of occurrence. So let's say we think there is 35% chances for 4% to come. There is another 15% chances that you will get a 9% return. That's how you go about calculating maybe the weighted average return over here. Let's say a 30% chances of getting a 5% return, and maybe a 20% chances of getting a 10% return. And this is how you determine maybe a weighted average kind of a return. So and then a definite question comes, how do we assign weights? One of the way to assign the weights could be with that interval scale. In a range, let's say 40% data is coming across in the past. So we say there is a 40% probability of this outcome to come. There is a 10% of probability of something else to come. So that is one way to determine the probability based on that interval scale. So we can determine probabilities based on that interval scale also. The other way could be based on the time of an outcome. Normally you give more importance to the recent past. So something that has happened recently, let's say if you are looking down to anticipate the cost of goods sold for a company based on the sales that it has generated. So obviously a 5-year down the line cost mechanism may not be that effective than the recent cost dynamics, because the operational aspects, maybe the company would have gone for an automation and other things. So things would have changed. So there could be a decay factor that you can use in terms of giving or assigning weights based on the time. Recent past is given more weightage compared to the older outcomes, because they are depicting the current scenario more. Another estimate for the return could be coming down from the geometric mean as a thought. So if you look upon to the formula of geometric mean, it is basically the root n of multiplication of all the possible outcomes and then taking an under root of that based on the number of outcomes. So that's how you calculate your geometric mean. But let's relate it within return terms. Let's say in 2010 you have invested $1 somewhere. On 2011 you've got, let's say, a 14% return on it. On 2012 you have got, let's say, a 12% return. 2013 was a sub year, so you just got, let's say, a 6% return, and maybe another 5% in 2004. So the thought of maybe the arithmetic mean is, on an average, what is the kind of return that you've got. So if you do 12% plus 14 plus 6 plus 5 divided by 4, that's more of an arithmetic mean, which is based more on a thought of simple interest concept. Now if, let's say, which is saying that every year you're getting that return on $1 only, but if, let's say, after a year your value is 1.14, getting a 14% return on $1 invested. Next year, if you do not withdraw the return, you'll get this 12% on this 1.14. So it is 1.14 multiplied by 1.12. Next year, this will be on 1.14 into 1.12, 1.06, and on. So you finally end up at 1.12 into 1.12, 1.06 into 1.05. So this is basically the future value that you have got by investing, let's say, $1 today. And you wanted to know on an average what kind of return that you can do that thing with putting the findings into your BA2 professional calci. Put -1 as the present value and put the future value as the multiplication of this final outcomes. Put n as 4 and calculate the rate, which will be your compounded rate over a period of time, the kind of a geometric mean kind of thing. If you put it into terms of a formula, it is PV equals to, or rather say FV is equals to PV 1 plus R raised to the power n. In this case, my future value is 1.14 into 1.12 into 1.06 into 1.05, which is equals to 1 into 1 plus R raised to the power 4. So what we are trying to find out is this R. On an average, what is the kind of a compounded return annually you have got into an investment over a period of times, and this is what you refer as again your CAGR, compounded annual growth rate. If you have to calculate this thing, it will be root 4 1.12 into 1.14 into 1.12 into 1.06 into 1.05 minus 1, which is equals to your R, which you refer as your geometric mean. So when it comes to return, you calculate the geometric mean as root n 1 plus R into 1 plus R 1 R2 1 plus R n minus 1. So when it comes to return, you calculate your geometric mean as 1 plus the expected return or 1 plus the return that you have generated over a period of time. You compound that and then you subtract the initial $1 of investment. When it comes to return, why we always go with 1 plus to calculate the geometric mean is because returns can go negative, and if there is a negative return in a given year, let's say -5%, when you put that into an under root, the entire value will get negative and you cannot get the root of a negative value. So when it comes to return, because the returns can go negative, we always do calculation as 1 plus the return into 1 plus the return. Root n minus 1 is how you calculate a kind of an average compounded return. In this case, this is a compounded annual because we have taken the period as annual only, and so the broader difference basically that we can say about between arithmetic mean and geometric mean is arithmetic mean talks more about simple interest only and geometric mean talks about compound interest. So let's talk about another category of determining the return, or maybe an expected value, or maybe an average out over here, and that's where we talk about the harmonic mean. Among the last week, let's talk about harmonic mean now. Let's say if an investor is investing $10,000 every month from past 3 months and into a mutual fund scheme. So this is kind of a SIP, systematic investment plan, and the NAV for this scheme in the first month was 8 per unit, 9 in the second month, and in the third month it was 10. And you want to know the average costing, what per unit has come to the investor. So we cannot go like 8 plus 9 plus 10 divided by 3. No, that would be a wrong thing. We need to know the total number of units and the total cost. To know the average cost of per unit, what we need to do is we need to know the total cost and the total number of units. So the total number of unit in the first case would be 10,000 divided by 8, let's say x. For second month it is 10,000 divided by 9, let's say y. And for the third month, let's say it is 10,000 divided by 10, which is z. So the average cost per unit will be 30,000 divided by x plus y plus z. Or let's say 30,000 divided by 10,000 by 8 plus 10,000 by 9 plus 10,000 by 10. You take 10,000 common, it is 3. 1 upon 8 plus 1 upon 9 plus 1 upon 10, and what you get is what you refer as your harmonic mean. So the thought of harmonic mean is not that complex. What we basically are saying is it is nothing but n divided by 1 plus x1, 1 plus x2, 1 plus x3, 1 plus xn, and you're getting basically the average cost per unit. Let's say if rather than investing 10,000 in the second month, you would have invested just 5,000, then it will be 25,000 divided by the total number of units that you would have got from the investments. So we've talked about the return measures at this point of time. So guys, till this time we've talked about the return aspects when it comes to determine an investment decision and using statistical tools. And there could be other ways of determining the expected return from an investment. Let's look upon to the other aspect, the risk. And the risk is with regard to this thing that, let's say if you're expecting XYZ return from an investment, let's say a 7% return or an 8% return by investing into a stock or so, the invariable thought comes across is, if I don't get this 7%, then what could I expect? And that is what we talk about, the uncertainty aspect of the expected return, the risk associated with it. See, remember, we took past as a basis to determine the expected return, like on an average what kind of a return you have got in past. You took that as a base and said that this is something that we can expect in future. So when it comes to anticipating the risk aspect, again we can go back to the past and look upon what have been the actual observations or actual returns that particular investment or stock has generated, and we can compare that with the average and see that from the average this is how much we have deviated in the past, and on an average the same deviation we could expect in the future. So let's look at some of the measures to calculate the risk associated with an investment, and one of them would be, the broadest of them would be the range, which is calculated as highest value minus the lowest value. So if let's say the highest return over the past 15 years would have been, let's say 25%, and the lowest, let's say, are -5, so your range is of 30%. Now, why we say this is a very broader measure? Let's say over this past 15 years, this stock has generated on an average a return of 18%. And that's where we say range is a broader measure of anticipating the risk, because how do you interpret it? From that 18%, let's say you've gone, because your range is 30%, let's say you say 15% up or down. And if you do that, you find out that your highest return could come down to, let's say 33%, which in the past were only 25%. So it at times becomes confusing also. The other way to maybe anticipate the risk could be by moving to the mean absolute deviation. In that case, what do we do is, let's say we have certain values of x in the past. We say, let's say we have values like 4, 9, 5, 10, and the average that we're getting is 7. So you expecting a 7% return in the past, or on an average you've got a 7% return. So you're expecting that in the future. Now let's see what have been the actual outcomes and how far has your actual result were there in the past from the expected value. So what do you do is xi minus x bar, what you get is minus 3 here, plus 2, minus 2%, and maybe another plus 3%. Now the thought is that in the past, let's say you have deviated minus 3 at one point of time and plus 2 at one point of time. So you think about taking maybe an average of it and say on an average this has been the deviation of actual values from the anticipated or the mean in the past, and this could continue. But when you go down to take an average of it, you need to sum it across, and when you sum it, the value would come as 0 because you've got the mean of 7, and the sum of mean deviation will always be 0. That's why 7 is your mean. So what we do is we take absolute deviation. We consider any deviation equal whether it is positive or negative. When we go about that, we get 3%, 2%, 2%, another 3%. The sum of that comes at 10. On an average, you say 2.5% is your deviation. So on an average, in the past, the actual returns have deviated by 2.5% from the mean. So we can expect the same deviation to continue in future, and that is how you interpret risk. You say at a 7% expected return, which is expected to deviate by 2.5% plus and minus, and which gives you a range of, let's say, 4.5% to 9.5%. And that is how you interpret risk. Risk does not mean, let's say, a 7% return and a 2.5% risk does not mean that 7% is the profit you'll get and 2.5% is the loss you're going to get. The 2.5% deviation here is saying this is by what amount the expected value could deviate from its mean, or the expected value could deviate by this fraction of 2.5%. In future, this is what you could expect. Remember, again, we are not saying what is the possibility of getting the expected return in this range of 4.5 to 9%. There could still be just a 50% chances of getting the expected value into this particular range of 4.5 to 9.5%. So when it comes to determining this thing, what is the possibility of an outcome into a particular range? Remember, we go back to that interval scale where we have framed the data, and based on past outcome we say this is the percentage of data which has come, or the portion of data that has come into this particular range, and you could expect the same to continue in future. So you might have to go down to that interval scale and find out what fraction of data has, or what number of observation from the overall has come into this range of 4.5 to 9.5%. You can assign that as a probability as 50% chances of getting the expected value into 4.5 to 9.5% range. So when it comes to determining the risk, from mean absolute deviation we can go to some other measure, which is standard deviation. So the thought is, let's say if you have to make this deviation positive only, xi minus x bar, we've made it positive by taking an absolute value. The other way to could be by is just squaring the difference. That is xi minus x bar's whole square you can take, which is, let's say, 9% square, a 4% square value, 4% square, and 9% square. So the total comes at 26% square, and you take the average as 6.5% square. Now the only issue is my unit of return is in percentage terms, and the unit of risk that I have brought in terms of average square deviation is into percentage square terms. So we can go down and take an under root of it, which comes out at 2.55%. So the squared value is what you refer as your variance, and the under root of variance is your standard deviation, denoted by the sign sigma. We say our variance is equals to summation xi minus x bar whole square divided by n, and the under root of variance is basically your standard deviation, which will be again into the same units as your return. And you can say from with an expected return of 7%, you can deviate by plus minus 2.55%, and that's how you interpret standard deviation. Very much similar to MAD, but then to calculate standard deviation we square the deviations, and to calculate MAD we just take the absolute of it. There is invariably a question which comes to everybody's mind: if we can work out with MAD, why is the need of going down to standard deviation? Why do you square the things across, then take an average, and eventually you'll have to take the under root to determine what is the average deviation which the stock has observed in terms of on an average basis the actual values from the expected values in the past. So the and there is always a proven fact by a lot of people also, where they say that standard deviation is a better measure of risk compared to MAD. So better measure of risk. Why is that so? Let's see that with maybe another example. Let's take an example to understand why is standard deviation a better measure of risk compared to mean absolute deviation. Let's say we have two set of deviation as 5 and 6, so the total is 11, and the other set of deviation is, let's say, 10 and 1, the absolute deviations, and the total is 11. So in both the cases, because the total deviation and the number of observations are same, we will have the MAD as same as 5.5%, right? On the other hand, we invariably can see from the data itself that in, let's say, array B or array 1, in the variable B, there is more deviation because it is deviating around 10% or at one point of time. So there is relatively a bigger risk in stock B compared to that of A, and standard deviation captures this far better, because the square of a bigger value will be a bigger amount and square of a smaller value will be a smaller fraction. So let's say what will be the values when you talk about squaring it across. So it is 25, which is the square of 5, so you get 36, which is square of 6, and the total is 61. You take an average of this, that would be 30.5, and then you will take under root of this value to determine your standard deviation, which will be, let's say, 5.6 odd percent or so. With B, 10 square will be 100, 1 square will be 1, so the total is 101. Divide by 2 will be 50.5, and when you take the under root of this will be somewhere around 7 point, that's a 1 odd percent. So when you see that the standard deviation is bigger here in stock B, signifying that is more risk in stock B compared to that of stock A, which MAD invariably fails to capture, and that's why we say standard deviation is a better measure of risk compared to mean absolute deviation. Now till this time, if you could remember, what we have used as a formula is sigma. So we're talking about a population variance. When you talk about a sample variance, the only difference we need to do is, rather than taking in the denominator as n, we take n minus 1, and we subtract this 1 because of the sample mean. We presume that the sample mean could be part of the sample itself. If that is going to be the case, the number of unique deviation will not be n, but rather n minus 1. Let's talk about a common application of expected return and risk. So there are, let's say, two stocks, stock A and B. The expected return of stock A is 18 and that of B is 24, and the variance of stock A is 25, or rather say the variance, the standard deviation of stock A is 25 and that of B is 35. So if you have to pick whether to go with stock A or stock B, as we said, whenever it comes to a comparison, whether A is better than B, one of the best way to go to that is use a ratio scale. So we're going to talk about two important ratios here. One is CV, which is coefficient of variance, calculated as sigma upon mean. So for stock A, your coefficient of variance will come as 1.35, and for B it will be coming as 1.4. Now let's look upon the formula. The formula has a base which is the mean. So we interpret the coefficient of variance of 1.35 for stock A as, for 1 unit of mean or return, you are required to take 1.34 units of risk. Let's say the unit of return is percentage. So we can say it this way: for 1% return in stock A, 1.34% is the risk. For the same 1% return in stock B, 1.4 is the risk. So the lower the better. We'll give, let's say stock A is rank 1 and stock B is rank 2. Now the other measure could be going to another ratio, which is Sharpe A, calculated as expected return minus RF upon standard deviation, where RF refers to the risk-free rate. Now Sharpe comes with an added thought. Let's say the risk-free rate is 8%. So what does the Sharpe's ideology goes is, for this stock A's 18% return, you're not basically taking the 25% risk, because out of this 18%, 8% you can get without taking any risk. So basically you're taking this 25% risk for the additional 10% return and not the 18% return. So in that case, you calculate Sharpe A for stock A as 0.4 and for stock B, it comes at around 0.46. Now in the Sharpe A, the denominator is the risk. So it is always interpreted in terms of risk. For 1 unit of risk, we say for stock A, you can expect 0.4 unit of excess return. And let's say if the unit of risk is percentage, for 1% risk, 0.4% of excess return is available in stock A, and for that same 1% of risk in stock B, 0.46% of excess return is available. So we'll give, let's say, stock B as rank 1 and stock A as rank 2 in this case. So that's based on the Sharpe's ideology. Now Sharpe is good for returns because you have a risk-free benchmark you can get, but then CV comes handy for other things also. Let's say you want to calculate the CV for sales of a company, so you'll have the average sales and the deviations, but there is nothing like a concept of risk-free sales, which is basically there with returns and expected returns only. The CV can be used at multiple places, but Sharpe is more to do with return determination. And there are other performance evaluation ratios like the Treno measure, the Jensen alpha and the M square, which we will be discussing into the portfolio theory part 2 curriculum of CFA level 2. For this point of time, let's keep it to this only. For any queries of yours, you can always write back to us. Thank you.